Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the real-time clock. So we will see that what is RTC or what is a real-time clock and how this RTC works. And we will also see the structure of this RTC and what are the different applications of the RTC. So as its name suggests, this real-time clock is a digital circuit which keeps the track of the time in a human-readable format, and it tracks the time even when there is a power failure or the power supply is off. So as you can see in this picture, a little battery is also attached with this real-time clock. That means even if there is a power failure or the main supply goes off, then this battery can provide the power to the RTC, and this RTC can work on this battery even for many years. So this real-time clock is used in the personal computers, smartphones as well as the servers, and it is also used in many embedded systems as well as the IoT applications. Like it is used in the surveillance camera, thermostats and even in the smart meters. So in early days, when the internet was not so common, in those days, this RTC was very essential to keep the track of the time in the personal computers, digital watches as well as in the camcorders. But nowadays if you see, then these electronic devices can have access to the internet as well as the GPS. And once they are connected with them, then they can access the accurate time. But when such devices accesses the time through the GPS or through the internet continuously, then they can draw a lot of power. And this is specifically an issue with the battery operated devices, like most of the devices which is used in the IoT applications. Moreover, when such devices are not connected with the internet or the GPS, then to keep the track of the time accurately, they need the real-time clock. That means for the battery operated devices, to reduce the power consumption and to keep track of the time when there is no internet or the GPS access, this RTC is very much required. And that is why this RTC is used in most of the applications where we need to keep the track of the time. So these RTCs can be built into the microcontroller or the microprocessor, or it can be connected externally to the controller via the serial interface. So if you see the built-in RTCs in the microcontroller, then typically the current requirement for this timekeeping function is in the microamperes. While if you see the operating current for the standalone RTCs, then it is typically in the nanoamperes. And that is why they are very much suited for the battery operated devices. So now, let us see the internal structure of the RTC and let us understand how this RTC works. So for timekeeping, this RTC needs the stable clock source, or basically it requires the oscillator. So typically a quartz crystal is used to generate the stable clock source, and mainly a quartz crystal with the oscillation frequency of 32.768 kHz is used. Now the reason for selecting this specific quartz crystal is that if you see this number, that is 32,768, then it is the power of 2. That means using the divider circuit, it is easy to generate the 1 Hz frequency. So we can say that this 32.768 kHz is equal to 32768 Hz. So here, using the frequency divider circuit, it is easy to generate the 1 Hz signal. Moreover, this frequency is beyond our audible range. Because if you see the audible range for the humans, then it is from 20 Hz to 20 kHz. And that is why we cannot hear the vibration of this given crystal frequency. So that is another advantage of using this frequency crystal for the oscillations. So like I said, apart from this crystal oscillator, we also need a frequency divider circuit to generate the 1 Hz and the other clock frequencies. So typically, via the output buffer, the one of the output of this frequency divider is available at the output pin. And in most of the RTCs, it is typically referred as the square wave output. So using the control register in the RTC, it is possible to select the output frequency of this square wave. So very shortly, we will also see the purpose of this output. But apart from that, the frequency divider also generates the 1 Hz output. So this output goes to the clock and the calendar registers, which is also known as the timekeeping registers. So as its name suggests, these registers stores the time, date, month and the year information. And through this 1 Hz signal, these registers are getting updated at the every second. So using the serial interface through a microcontroller or the microprocessor, it is possible to configure the date and time of these registers. and using the same interface, the controller or the processor can access the current date and the time information. So typically, the serial interface which is used for the communication is the I2C. Apart from that, to power up all the circuitries, we also have the power control block. So whenever the external supply VCC is available, then the RTC will operate on the external supply. But if there is a power failure or if the external supply voltage falls below the battery voltage, then the circuit will operate on the battery voltage. So this power control circuit will decide all these functions. So apart from that, the RTC also has the alarm, status as well as the control registers. And to sense the ambient temperature of the RTC, it also has the temperature sensor. So far, briefly we have already seen the function of some of the blocks. But now, let us understand the function of some other blocks in detail. So like I said, the clock and the calendar registers are also known as the timekeeping registers. And these registers keeps the track of the time as well as the calendar function. So if you see the timekeeping registers, then they have a separate registers for the second, minute and hours as well as for the days, weeks, months and the years. So the seconds register is getting updated at the every second. And as you know, it will go from the 00 to 59. And as soon as the value of this register reaches the 59, then it will get reset to 00. And immediately, the minute register will get updated. That means this minute register is getting updated at the every 60 seconds. So similar to the second, this minute register will also go from the 00 to 59. And as soon as it reaches the 59, then it will get reset to 00. And at the same time, the hours register will get updated. So similar to the minute register, when the 24-hour gets completed, then the hours register gets reset to 0 and this day register is updated. And subsequently, the other registers are also getting updated. So these calendar registers also have a logic to check the leap year and accordingly, the number of days in the months are getting adjusted. So typically, the data that is stored in these timekeeping registers is in the BCD format. So apart from the timekeeping registers, the RTC also has some control registers and the registers to generate the alarm. So using these registers, it is possible to generate the different alarms. And apart from that, with the help of the control registers, it is possible to configure the RTC. Like by setting some bits in this control register, we can change the frequency of this square wave. So this square wave output can be used to generate the precise interrupts. That means the square wave output can be programmed to the specific frequency like a 1 Hz and the main device like our microcontroller can use this signal to trigger the interrupts at the regular interval. So this can simplify the task like updating the system clock or performing the periodic actions without constantly polling the RTC for the time. Apart from that, in some applications, it is required to synchronize multiple devices with respect to time. So this RTC square wave output can be used as a reference signal for synchronizing these devices. And in this way, it is possible to maintain consistent timing between these devices. So apart from that, sometimes the square wave output can also be used to drive the peripheral devices like the LEDs. So these are some of the use cases of the square wave output of the RTC. So apart from that, each RTC also consists of the temperature sensor. And in fact, this temperature sensor is very important for maintaining the accurate timing. So as I said earlier, typically a quartz crystal of 32.768 kHz is used to generate the precise clock signal. Now these crystals are calibrated in the factory to oscillate at this targeted frequency. But if you see the tuned frequency, then it will not be perfectly accurate. So the accuracy of this quartz crystal, or effectively the accuracy of the RTC, is mentioned in the ppm, that is parts per million. That means if the accuracy of the RTC is plus 20 ppm, it means that at every 1 million second or roughly 11.57 days, the crystal or the RTC will move ahead by the 20 seconds. Or in a year if you see, then it will move ahead by the 10.5 minutes. So to reduce this timing offset during the fabrication, according to the accuracy of the quartz crystal at the given temperature, the frequency of the crystal oscillator is tuned using the load capacitors so that it provides the accurate frequency. But even with this tuning, because of the aging as well as the temperature variation, the oscillation frequency may change. So typically, with the aging, the change in the frequency of the crystal oscillator is very low. But with the change in the temperature, the oscillation frequency can change continuously. And in the applications where the accurate timekeeping is required, this change in the temperature can lead to the error in the timekeeping. So to avoid that, the temperature compensation is very much required in the each RTC, and that is why each RTC also consists of this temperature sensor. Now during the fabrication, while calibrating this RTC, it is easy to get the data like how the crystal frequency changes with the temperature. For example, if the temperature increases by the 5 degree, then let's say the frequency changes by the 1 ppm. And likewise, we may have a data over the certain temperature band. So we can use this data to correct either crystal frequency or to correct the error in the timing. So this frequency divider block is basically a frequency divider and the control block, where we also have this additional control logic for the temperature compensation. So as the temperature of the RTC goes above or below the calibrated temperature, then the reading of this temperature sensor is stored in the internal register of the RTC. And based on the stored value of the temperature and the calibrated data, the controller in the RTC can predict the estimated frequency of the crystal oscillator. And based on that, it is easy to predict whether the count value in the timekeeping register is less than 1 second or more than 1 second. So there are a couple of methods which are typically used for the temperature compensation in the RTC. So in one method, due to the change in the temperature, if the frequency of the crystal oscillator increases, then the 1 count is less than 1 second. Let's say now a 1 count corresponds to 0.9999 second instead of the 1 second. So now in the timekeeping register, when the count value reaches the 10,000, then it actually corresponds to 9999 seconds. So in such case, what the timekeeping register can do, it can repeat the count value after the 10,000 counts. And in this way, it can compensate for the time. Likewise, if the frequency of the crystal oscillator reduces, then the 1 count is more than the 1 second. So let's say now the 1 count is equal to 1.001 second. So now in the timekeeping register, when the count value reaches the 10,000, then actually it corresponds to 10001 seconds. So in such case, what the timekeeping register can do, it can increment the count value by 1 after the 10,000 counts. And in this way, it can compensate for the lost time. So in this way, it is possible to minimize the effect of the temperature. But the disadvantage of this method is that it takes a longer time for the compensation. So typically, a change in the temperature is a slow process. But this way of compensating a temperature or effectively compensating a time is even slower. And by the time the correction happens in the time, it is quite possible that the ambient temperature of the RTC is already got changed. So this is one method. On the other hand, in the frequency divider block, if it is possible to change the prescaler to the different values, then by adjusting the prescaler value in between, it is also possible to fix the timing of the RTC because of the change in the temperature. For example, let's say because of the change in the temperature, the clock frequency of the crystal increases and it becomes 32.7712 kHz. Now typically, to generate a 1 Hz clock signal, the prescaler value in the divider circuit is kept 32768. And with this prescaler value, if you see the timing of the each count, then it is equal to 0.9999 second. That means if we divide this crystal frequency with the prescaler, then we will get the frequency which is slightly more than 1 Hz. And in the timing if we see, then that is equal to 0.9999 seconds. So here, to adjust the timing, we can change the prescaler value at the every fourth interval. So here, for the first 3 intervals, this prescaler is kept 32768. That means if we see the timing of the first 3 slots, then that is equal to 0.9999 seconds. And now in the fourth slot, now the prescaler value is changed to 32781. That means now the timing of this fourth slot is equal to 1.0003 seconds. So here, roughly after the fourth clock cycle, the timing is equal to 4 seconds. And in this way, it is possible to do the temperature compensation in the RTCs. Apart from that, sometimes, to make the RTCs even robust, the temperature compensated crystal oscillators are used. So these are some of the temperature compensation techniques that is used in the current RTCs. Apart from that, some current RTCs also consist of the watchdog timer and the temper detection circuits. So using the watchdog timer, if the controller or the processor is stuck somewhere during the execution, then it is possible to reset it. For example, the RTCs having a watchdog functionality can start the watchdog timer with the predefined count value, or basically they can start the timer with the predefined time. So if the controller or the processor does not reset this watchdog timer before this predefined time, then the flag can be raised and accordingly some necessary action to reset the controller or the processor can be taken. Similarly, some RTCs also have the ability to detect and the timestamp the temper attempts. And this feature is specifically useful in some devices like the smart meters. So this is the basic block diagram and the basic functionality of the real-time clock. So I hope in this video you understood what is real-time clock, how it works, and what are the different applications of the RTC. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.